Okay, please turn to Worksheet 11, the notes page in your packet. And now we're going to move on and look at a pH of a mixture of weak acids. And our problem says to calculate the pH of a mixture of 2.00 molar formic acid, it's given the Ka, and 1.5 molar hypobromous acid. What is the concentration of both of the hypobromite and the hydroxide ion at equilibrium? So now, listing this major species is going to take on a whole new meaning. So our major species now, obviously it's always water, but we're going to include this formic acid, so HCOOH, and it's 2.0 molar, and HOBr, and it's 1.5 molar. Now, choose the species that can produce H+, and write balanced equations for the reactions producing H+. Well, we know they're both acids, so they're both going to produce H+. So we'll have HCOOH yields H plus HCOO minus. Remember from earlier that that's the hydrogen that comes off. And then HOBr yields H plus OBr minus. All the same steps that we've done so far. Using the values of the equilibrium constants for the reactions you have written, decide which equilibrium will dominate in producing H+. So I have HCOOH, and that has a Ka equal to 1.77 times 10 to the minus 4th. I have HOBr, and my Ka is equal to 2.06 times 10 to the minus 9th. My one that will dominate is my HCOOH. And this dominates because it's the larger Ka value. It has nothing to do with the concentration. It has the larger concentration, but that wouldn't matter. It totally has to do with comparing the Ka values. And so it says using the values of the equilibrium constants. That's why we've been doing this step 3. Up until now, we haven't had to make a decision, but now we finally did. So my dominant equilibrium is the HCOOH, the formic acid, and so I'm going to write my equilibrium expression. So it's going to be Ka is equal to 1.77 times 10 to the minus 4th, which is equal to H plus HCOO minus over HCOOH. There's my equilibrium expression. Now, move on to step 5, and this is our ice chart. List the initial change and final concentrations of the species participating in the dominant equilibrium, that ice chart. So, we have HCOOH yields H plus HCOO minus. I'll set up my ice chart. My initial concentration of the formic acid was 2.0 molar. And my initial concentration of those two was 0, because when I put it in the solution, there would be none of it in existence. This is going to go down by a factor of x. These will increase by a factor of x. And now it's 2.0 minus x, and x. Notice I don't even have to take into account that hypobromous acid. It's not the dominant equilibrium, so it's not going to be factored into our problem. This is why we're doing these steps, because I'm teaching you how if you know these steps, it will really solve any problem that you have. You're going to substitute the equilibrium concentrations back into the equilibrium expression. So 1.77 times 10 to the minus 4th is equal to x over 2.0 minus x. And then, since it's so convenient, we're going to solve for x the easy way. So we'll do this 1.77 times 10 to the minus 4th is equal to x over 2.0. We end up with x squared is equal to 3.54 times 10 to the minus 4th, and x is equal to 0.0188 molar. So don't forget to take the square root once you multiply by that 2.0. If we're going to use that easy way, we have to do that 5% rule. So we're going to take 0.05 times my initial concentration, which is the 2.0 molar, and we end up with a 0.10 molar. 0.10 molar is greater than the 0.0188 molar, so we can write 5% rule checks out. Okay. And then it says 9, and this is where 9 is going to deviate from what we've done before. It says calculate the hydrogen, the pH, and whatever else it asks for. So our hydrogen ion's already done because that's our X value. So X, which is equal to the H plus, is equal to 0.0188 molar, which means my pH is equal to the negative log of 0.0188, which is equal to 1.73. It wants us to do the hydroxide. So 1 times 10 to the minus 14 is equal to 0.0188, which is my hydrogen, times the hydroxide. This is my hydrogen times hydroxide equals 1 times 10 to the negative 14th. So my hydroxide ion concentration, in this case, is 5.32 times 10 to the minus 13. Now, if you remember, the problem also asked us to solve for the hypobromite ion. So, to do that, we look back at that reaction. We had written the equilibrium expression. We know our Ka for that is 2.06 times 10 to the minus 9. And if you remember from earlier in our problem, we had this reaction written. And I'm just recopying it here so that you can see it visually. And so if I write my equilibrium expression, I have H plus, I have OBr, and I have HOBr. I'm going to plug in my values. I have 2.06 times 10 to the minus 9. I know my H plus because I solved for it over here. It's the dominant equilibrium. So 0.0188. OBr is what I'm solving for. And I can just go ahead, because it's such a small value, go ahead and use my initial concentration of HOBr, 1.5. I plug that all in, and I can solve for my OBr, which ends up being 1.64 times 10 to the minus 7.